Hi, everyone. The talk, as we know it, is forget the 1 billion roads challenge. Let's solve the iZombie endless. Great. A brief note about me. My name is Fanan, and I'm a software engineer at Meta. I previously worked at Lemfi, Ticks, and Holotags. I'm obsessed with designing high throughput systems and good code architecture. And this is why I love Go so much because it allows me to do both. Outside of software engineering, I love swimming, shouting along to Afrobeats, and I enjoy walking on the runway. I do model on the side. Now, what to expect? In this talk, you will learn how to simplify overwhelming problems. You learn about one creational design pattern, some concurrency design patterns, and a little bit about some of the packages that Go gives us to handle concurrency. What you should not expect from this talk is a deep dive into the simulation engine because no time for that in the talk, and I've also not finished it. And then deep dive into profiling and performance. So we won't go too deep into all of these things, just pretty surface level on the concurrency architecture. Great. So what is the iZombie Endless? The iZombie Endless is a puzzle minigame in a Plants vs. Zombies minigame. It involves finding the best combination of zombies that would allow you to eat all the brains on each row, which are these pink little brainish looking things here in this video. And every zombie has a sun cost, as you can see, from 50 to 350. And you're supposed to use as little sun as possible, right? So currently I'm stuck at 19. I think yesterday I reached 20 for the first time. But however, I thought, let me create a computer to fight a computer. So that's why we're here. Great. So how do we solve these permutations? Right. So my first intuition was obviously to generate all possible zombie combinations and select which one solve the game with the least sun. And this is pretty much how chess engines work, where they try all possible moves and then they simply select the best outcomes. And if you're not familiar with permutations and combinations, it's simply a branch of mathematics that helps us know how we can, select items, right? And combinations deal with unordered arrangements, while permutations deal with ordered arrangements. So if the order matters, you'll be doing permutations. And because in solving this game, the order does matter, we are doing permutations. And now we do have a problem, however, which is chess is a 2D game. Well, we have a 3D game and we need to simulate, this 3D world and the 3D motion. So how do we do that? And so for that, we're going to take a cue from animators. In animations, what you usually have is a series of 2D frames that are being, merged together to generate a 3D view and make things move. And so we'll be taking a cue from that to represent our world in a 2D code. We'll be using Golang, like I've said from the start, and we're going to model every frame as a struct, and that struct will contain the fields that hold the representation of the game. Great. And so look at what we have here. We have a cell with a row and column that specifies where the position of this cell is, what plants are on the cell, what zombies are on the cell. We have a frame struct, which consists of a board, which is a multi-dimensional array of cells, amount of sun left, amount of sun used, the number of iterations the frame has been through, and the zombies that were inserted into this frame. And then we have the interface for the frame and the interface for the zombie. So we can see how the frame holds the representation of the bird. And for every iteration, we simply just update the positions of, the items here. And that gives us like, 3D-ish simulation. Great. Now, if you look at the interface for frame and zombie, you'll notice that we have copy methods on them, right? And this is a creational design pattern known as prototype design pattern. And in prototype design pattern, what you simply do is you create new objects by cloning an existing object and then modifying the object. And you do this where creating a new object is like really expensive, or there's just a lot of recreation going on, like we do here. And so this is why we are leveraging the um, prototype design pattern. Great. Now let us design our pipeline. Now we need a pipeline because we have to generate all possible zombie simulations, right? And then we need to simulate them and then select the most efficient frames from all of these simulations. So before we have a go into doing that, let us run numbers. So let's look at the game field. We have 9 rows in total, and we have, 9 columns in total and 5 rows. However, if you look at this red line tells us where we can place our zombies. And this red line is the 6th column. So we can place zombies at the 6th column. However, you place it like right in front of the 6th column. So let's just take out everything from the red line and focus only on the first five columns. So we have five rows, we have five columns for which we're going to need to run our simulations. However, if you take a look at the video once again, you notice that the zombies aren't just jumping from cell to cell, they're walking, they're taking three steps to cross a particular cell. And so that tells us that if we want to accurately simulate how the movements would be, we would need to divide each cell into three more subcolumns, right? And so that gives us a total of 15 subcolumns because five cells times the three subdivisions that we have. So 15 subcolumns, everything still looks okay, but we're going to run into a bit of a problem soon. Great. So 15 subcolumns, and now we have nine zombies. The 10th zombie here, Gargantua, is you never encounter it in the iZombie Endless, so don't bother. So we have nine zombies: Imp, Cone, Pole, Bucket, Bungee, Dia, Ladder, Football, Disco. However, because of certain constraints that we're going to see along the way in this talk, let's ignore the Disco zombie. And personally, I rarely ever uses the Disco zombie. So we have only eight zombies. So 15 subcolumns, five rows, eight zombies. What does that give us? Um, so if we have five rows to choose from and eight zombies, then that means every time we need to place a zombie, there are five times eight ways to do that, which is 40 choices. So 40 ways to place a zombie on the board. Right now, that sounds simple, but remember that every zombie is taking a step, and we're doing best permutations, right? So for every step, we want to imagine that we can potentially place a new zombie on the board. And so for every step, we're going to have 14 new ways in which we need to select. Now that gives us a problem because that number is going to grow exponentially. So look at this. The first step, we had an empty yard and then 40 different ways to place a zombie. Now, each of these 40 different ways is going to generate 40 more different ways. And so by the second step, we have 1,600 ways to place zombies. By the third step, we have 64,000 ways. Now, remember that we have 15 steps minimum, right? And so 40 raised to the power 15, following the trend of this exponential growth, we could potentially have 1.1 septillion frames to simulate or to process in our pipeline. Now, that's a really, really big number, right? Because one septillion is 1 trillion trillions. So we cannot pull all of this into memory, and processing this is going to take a really, really, really long time. So what do we do when we have such huge constraints to deal with and it doesn't seem like we have the capacity? We don't. So when you can't do everything, don't do it all, right? Now, oftentimes, whenever we're faced with a problem, our first intuition is always to try to do absolutely everything to solve it. But this doesn't always work, right? You truly can't do everything and you need to let some things go. And we see this happening today, even in real production systems. So people rate limit. You try to query an API, it tells you you have only 100 calls per minute, right? People give out capacity constraints. Right now, Snapchat says if you have more than 5 gigabytes in your memories, you need to start paying for it, right? And then some people do tired product rollouts. So when Twitter was releasing the voice note feature, they only released it to a few set of people before it was released to every single person. So you can solve for a particular set of users first and then roll out for everyone. So don't do everything if you can't. However, we must do something, right? So one thing we can do is to leverage what I like to call approximate solutions, in which they will never be as accurate as a true solution, but they get us close enough to what we need to do. And so how can we do an approximate solution here? One thing we can do is realizing that we don't have to solve every row at the same time, right? We can actually solve row by row, and that's actually how I tend to solve most of the games. So you can see here, I started with the center row and then the topmost row, and then solve the rest of the rows. So we can solve one row at a time. And this is why I said we should ignore the disco zombie, because the disco zombie needs three rows to simulate. So if we're simulating one row at a time, we can use it. So ignore it. So we have eight zombies to choose from, one row instead of five rows. So it's no longer eight times five, it's now eight times one row. So eight rows to simulate per time. And if we apply the exponential growth, 8 raised to the power 15, the maximum number of frames we could have will be 35 trillion frames, which is pretty comfortable. There are 35 gigabytes RAM computers as of today. So we could potentially fit all of this into memory, although we shouldn't, but we could. Great. So this is a much more comfortable number. The second thing we can do is to leverage the attributes of the system itself to cut down on the things we need to do. So in this case, I leveraged the sun, right? And if we take a look at the diagram that we have here, we start with an empty frame with 200 sun and no zombie. And these are the potential zombie combinations or zombie placements we could have after the first frame. Now, if you take a look at the football zombie, you notice that the amount of sun left after placing it is 25, right? And ideally or theoretically, we should be able to have 8 more frames generated here, but we have none. And that's simply because the minimum sun required to place a zombie is 50. That's Im zombie, and we have only 25. So this is where the end of the line for this branch of our tree goes, right? In the ladder zombie, we have something similar, but at least in this case, we still have 50 sun, and so we can still place an Im zombie. But after the Im zombie, that's the end, no more frames. Even though theoretically, if we had infinite sun, we should be able to have 8 more frames generated and keep going, but in reality, we don't. So you can see that the amount of sun you provide restricts the depth of the tree. And so if we give less sun to the simulation engine, then we're going to have less frames generated in total, just because the engine just cannot generate zombies if there's no sun. And so when we do that, we say 500 sun, for instance, at most the average range we'll get will be between 4 to 5 steps. That'll be the average depth. And for that, that's like what, 32K frames, all the way from 1.1 septillion. And if we go all the way to like max it can be, which is 10 steps, because Im zombie 50 divided 500 divided 50 gives us 10. That's 1 billion frames. So still pretty comfortable amount. We have 32 gigabyte RAM laptops today, so we can fit this into memory. Great. Now let's go into actually design our system. So before we go on, there's this concurrency pattern that you're probably going to encounter if you're designing any concurrent system, and that is the fan in and fan out patterns. Now, fan out is simply when you have a pipeline and multiple nodes are reading from it, and fan in is simply when you have a pipeline and multiple nodes are writing to it. And so we're going to just leverage this to create a very naive design, which is what we have here. Pretty confusing as it should be, because this is a very bad design. You have a starting frame, right, which goes into a queue that holds all the frames. And then we have workers that reads from this queue, and they try to simulate the frame. And then they also try to generate, possible zombie combinations like we agreed on before. And they also try to find a solution. Now, this design is pretty bad because, one, there's no constraint on what's going to go on in this queue. It can run out of memory. And from our calculations, we've already seen how big the memory can explode to. We're violating single responsibility principle here, because this is doing everything, right? And it's also pretty hard to figure out how to scale the system, because again, everything is just clumped into one worker, no way to split them out. At best, what we're going to have to do is just, duplicate the workers. And even doing that at some point will lead us to bottlenecks. So we need a more intelligently designed system that allows us to estimate and predict scale of the system better. And so you should apply solid principles to system design. Great. So what does it give us? We have a new setup here where, first of all, we split the concerns of the queue. We have one queue for generating zombies, and we have another queue for simulating the frames. We have one set of workers for placing the zombies on the frame, and another set of workers for handling the simulation. Great. So that's as far as we split it to make the design readable. And now this new system is a bit more, it's better, and it's easier to figure out how we're going to scale this. And so let's take a look at that. So we know that we have a generate zombie queue. We place an initial frame in it. It gets read by a zombie generator worker, and that generates 8 frames at once. So that tells us that at the minimum, our simulate zombie queue should have a capacity for 8 frames. So it should be 8. And if we want the simulate zombie queue to be cleared as fast as possible, then we should also have 8 simulation workers. So 8 capacity zombie queue and 8 simulation workers, right? And then for the zombie generator worker, it already does its work in multiples. It generates 8 frames at once. So just simply divide, the amount of frames it can generate by the capacity of the simulate zombie queue, which is 8 over 8, 1. So you can see how this automatically like structures itself into where we see what we need to scale and how much we need to scale it. So if we wanted to increase capacity of the system, we know it's going to increase in a multiple of 8. So 8 times 2, for instance, will give us a 16 capacity zombie queue, 16 simulation workers, and then only 2 generator workers. Great. And we have a simple formula to then calculate the speed of our pipeline, which is the number of frames divided by the capacity of the pipeline times the simulation time. Now, how about the generate zombie queue? We haven't figured out what the capacity should be yet. So stay with me. We'll figure that out as we go on in this talk. Let's jump into implementation details. However, before we go on, I understand not everyone here is familiar with Golang as a language. So I just want to do a brief run on like some of the concurrency primitives that Golang gives to us. So the first thing is a Go routine. Now, a Go routine is just simply a function that is being run asynchronously. And you do that by saying the keyword go. So go full, go bar. We've made full and bar into Go routines right now. So that's just what Go routine is, asynchronous function. Channels. Now, a channel is simply a special data type in Go that's used to pass data between two Go routines. And the technical name is called a semaphore. Channels can be buffered or unbuffered. A buffered channel means that it has a capacity. An unbuffered channel means that capacity is 1. So, right, remember we need a capacity for simulation zombie queue. So we will be using buffer channels for that. And when you're passing the channel to a function, you can specify if it should be read only or if it should be write only. So which is what these lines that you see here are indicating. Great, and then we have select. Now, a select statement is simply a switch statement that allows us to choose between two concurrent operations. So here we're saying if we can read from this channel, read. If we can write to this channel, write. Whichever one is ready first, the select statement will pick that and execute. So that's just what select is. And then we have sync.wait group. Now, sync.wait group is just a way for us to synchronize our Go routine. So if you launch a Go routine in the main function, the main function can exit before the Go routine completes its execution. So a wait group allows us to specify to the main function to, oh, wait, hold up, there's still some Go routines being run. And then when the Go routines are done running, they call on wait group that done. And then that lets the main function knows that, okay, everyone is done. It's time for us to go. So great. Now we know about Go concurrency primitives. Now we know that we already need to constrain how many workers are being generated for our pipeline. And so we're going to be making use of a concurrency pattern known as worker pool. So worker pool is just a pattern for us to constrain how much workers we generate per time. And for the zombie queue, don't worry, we will get back to that, trust me. So this is what the worker pool pattern kind of looks like. And this is kind of like this is our main function. So this is the section for the worker pool. We just have like, number of workers we have. And for every worker, we obviously do the wait group, and then we send the Go routine to start running. And so that is the max number of routines that will ever be created for that worker. And so that's worker pool, nothing too complicated about that. And here we have like a section for aggregating the solution. So all it's doing is just reading from the solution queue, and then placing it into a map that lets us know where we found the solution. And we need a select statement here. Now we have a default case. What is going on here is just I'm trying to make sure that the system doesn't run infinitely. So I have like some timers checking for when last did we see a solution, and how long has this program run altogether. So if we don't see a solution after a specific amount of time, end program. If it's been more than 30 seconds, end program. So either ways, we know that the program would get terminated. Great. So let's look at our simulation workers. So for the zombie generation worker, simple algorithm, we read from the zombie generate zombie queue if there is a zombie, and then we try to place a zombie on the frame. And once we've placed the zombie, we send it to the simulate zombie queue. Simulation worker, we read from the simulate zombie queue, simulate the frame. If there is a solution, send to the solution queue. If there is no solution, duplicate the frame and send it back to the generate zombie queue so that the zombie worker can place a zombie on it. And this context of done is a way for us to ensure that if for whatever reason the main program says everyone needs to terminate and end now, this is how we do that. Sends out a cancel signal, and that would make sure that all Go routines stop. Great. So I ran, this initial design, and I guess with 100 Sun, I was able to get like a good solution. And these are actually correct solutions because with 100 Sun, you should be able to use imp zombie or 2 imp zombies or 1 pole vault zombie or 1 cone head zombie. However, when I got to 250 Sun, that generated like so many frames, and that ran into a deadlock because there was just so many things going on together. So why did we run into a deadlock? Well, the reason is because of the generate zombie queue that we've been ignoring all this while. So In reality, you can give it as much capacity as you want, but it's definitely always going to run out of capacity because the our pipeline generates frames in an exponential manner. Right. So usually in real world systems, when this happens, what we call it this is back pressure. That's when like our pipeline just has too much information going into it. And so one way that we solve back pressure is one, we can deploy additional resources. So increase the capacity of the queue as much as we want, or increase the number of workers that can process the frames so that we clear the queue as fast as possible. But again, I already know that this is going to be an exponential growth. So no amount of capacity will be ever be enough. So we can use that here. Additional option is to add a sink. A sink is just basically a temporary place to dump excess information, and then we can later come back and process it. But adding a sink to this was, going to complicate it a bit more, and honestly, no need for it. Then the final thing to do is just drop the overload. Like we learned before, we can do everything, don't do everything, aka rate limits. So what we do is simply whenever any of the queues are full, we just drop whatever frame we have that we're trying to send to it. And that's what the simulation worker did. So here we added a new select statement, and then we say, oh, if we can send to the generate zombie queue, send. If we cannot send to the generate zombie queue, then drop the frame. Now, this might look funny to you because it looks like it's nothing happening here, but that's because Golang automatically handles garbage collection. If this was a language like C++, you probably have had to do something like new frame dot destroy. So, but we don't have to do that. Golang automatically handles that for us. So yeah, we drop excessive information, and that solved the deadlock. Our program continued to run smoothly. However, I wanted to count the total number of frames that were generated, just so I can see for myself. And so to do that, in the main function, I created a new channel called count frames, and right, a new channel called count frames. Oops, sorry. Yeah, called count frames. And then here we try to send to that queue with in our simulation worker. So every time we have a new frame, we send it to count frames generated, and then we begin. Great. However, that sends me to another deadlock. And the reason why is just because there's just so many frames being generated at once. So in order to solve that, I had to then leverage a package called Atomic. And Atomic allows us to do lockless updates on shared resources, right? And however, the only drawback of this is that it only works on primitive types. So this is great for us because all we're doing is just counting, so which is good. And that was what helped me to solve this problem. And I was then able to count the frames. So here we have our lockless atomic counter. And then anytime we want to add a frame, we just call the add method. Same thing here in the simulate zombie queue frame counter add one. And once we're done, we call the load method, and that helped me solve the problem. Now, so everything was going good. We're counting frames. We don't have any deadlocks, but I wanted to do one last optimization, right? Our system works and we don't run into any deadlocks as we scale it. However, I felt that rather than just dropping every frame, why don't we just drop only the already inefficient frames, right? And so to do that, one, I chose to represent our solution heap as a max heap, right? And by doing this, it allows us to check for the least efficient solution in O of one time, right? And also because this heap is going to be read by the simulation workers and written to by the main worker, we also need a form of shared resource protection. And so I'm going to use a mutex. However, I'm using a special kind of mutex called a read-write mutex because we're going to be having a lot more reads and only one single write. And so this just fits well for our use case. So this is what we currently have. We initialize our heap. Whenever we want to write to the heap, we lock. Whenever we're done writing, we unlock. And we have this method to check if more efficient frame exists. And what it does is to read, acquire a read lock, read from the heap, and then unlock after reading. However, I ran into another problem. There was another deadlock that occurred. And I'm like, okay, what's going on here? Why are we having a lock contention even though I'm using a read-write mutex? And the reason is because our lock acquisition is not as atomic as possible. Now, what do I mean by that? If we look back at our previous code, which is what I'm showing on the screen here, We lock, we perform like one, two, three, four operations before we unlock, which is pretty dangerous to do. Um, and so if we look at this, that small space of time with a computer, because of how fast it's running, allows for a lot of contentions to happen and allows for our queues to get clogged. And so the only way to solve this is to make sure that our our utilization of the locks are as atomic as possible. So look at what we have here: wide range of operations happening before we unlock, and then we come down and we have a new and a better solution. So here in the new solution, we lock and then we immediately unlock after we've written. So compared to previous, in the previous time we locked, we push, we count, we check if it's greater than, we pop, and then we unlock, right? Well, in this new method, we lock and we push, and then we immediately unlock, and then we lock and we read, and then we immediately unlock, and then we lock and we pop and we immediately unlock. So we make sure that the operations are as atomic as possible. And when we did that, that solved our lock contentions and our deadlocks. And yep, and I was able to. I think this was I gave it 500 sun. Yeah, so as you can see, 375 sun used. These are all of the top five solutions that we got, and this is the number of total frames generated and number of solutions we found. So all the counts working, no deadlocks, and no issues. Great. So what have we learned? We've learned how to break down a tasking problem into smaller parts. We've learned how to leverage suboptimal solutions to, solve a problem when the optimal solutions would require too much resources. We've learned about the prototype creational design pattern. We've learned about fan in and fan out concurrency design pattern. We've learned about also guarding them with worker pools. And we learned about the atomic package, how to use it, when to use it, the fact that it performs lockless updates. And we've learned about read-write mutex, when to use it, why to use it, and pitfalls of using mutexes. Remember to be as atomic as possible whenever you're using mutex. Great. So thank you very much for coming to this talk, and I hope you learned a lot and you found it entertaining and insightful. Great. So I guess we can move on to the questions now.
Yeah, I think you finished a bit early, so yeah, the floor is open for questions and answers. So if you have any questions, please leave them in the Q&A box. Yeah. Okay, Fanan, we have a question. Someone asks, what are semaphores?
Right. So semaphore is just a technical name for what's the word? Um, okay, in concurrency, right, there's something we say which is don't communicate by sharing memory, share memory by communicating. So they're just mechanisms in concurrent architecture that allows you to communicate with that allows two routines to communicate with each other. So that's basically like the simple explanation on them. So channels in Go is just basically Go's types of semaphore. Yeah. Different languages, well, yes, like Erlang, have their own names and their own mechanisms and exactly how they work or how they're implemented. Yeah, I hope that that's clear enough.
Yeah, yeah, thank you. I think okay. Yeah, someone asked, okay, someone mentioned that they loved the talk, right? And would like if you could recommend a book on design patterns.
I did have a book I was reading. Just sorry, give me a minute. Let me see if I could find this. It will be on my GitHub, probably GitHub, where are my projects, repositories. Hope I find this as quick as possible. I don't have it in my head, that's why. Um, where was this? Oh my god, there's so much. I'm going to see where is this repo? Okay, design patterns with Go. Where what book was I reading for this? Okay, no, I don't. I don't have a book right now, but I would look for and I will send. Yeah. So, but yeah, I
Oh,
did have a book, but it's just not in my head anymore. Sorry.
okay, that's fine. I think when you remember, you can let us know
Yeah.
maybe during the networking sessions or something.
Yeah. Great.
Right. Okay. Someone also mentions that they know you didn't talk about the simulations, but they were wondering how did this relate to solving the game and were you simulating the 3D scenes?
Sorry, I'm not sure I get the question. Let me see. Um,
Yeah.
Right, right. Oh, right. Okay, so how does this relate to solving the game? So the simulation is actually the most important part of the game. And like I said, if you follow the talk, we don't obviously simulate. Everything is purely mathematical, right? So the frame basically holds the information about where every object is, and every object also has like its own algorithm for how it will move. So every time you iterate on the frame, based on the iteration of the frame, each item on the board can calculate, maybe depending on how it moves, either using projectile motion or using normal, distance times time calculations, right? It can know where it should be on the board at any specific time. So that's how it's related to solving the game, because it is the simulation that needs to run, and after the simulation runs, that's when you decide, did the zombie die, did the brain get eaten, um you know and that's basically the solution, right? So that's how it relates to solving the game. And no, I don't simulate the 3D game, the 3D scenes. What I just have is a representation of the board on the frame, and then I use mathematics to calculate where every item should be, if items interacted, what should be going on at any point in time. So basically, in this idea, the frames now act as like time. I don't know if you get what I mean. So let's say if I'm like walking down the road and I'm like, okay, at a speed of 1 kilometer per hour, at time t, where would I be on this lane, right? So that's something similar that I apply to the game. The only difference is, instead of time t, it's more like at frame x, where would I be based on my speed, my mass, and my current trajectory. So it's maths, coordinate geometry, projectile motion, all of that. Yeah. So that's just it. I hope I answered your question.
Yeah, so we have 2 more minutes. There are two questions. Okay, I think someone says, okay, for someone interested in learning Go, what book do you recommend?
Hmm. Um. So there's a Go book by Packet. They're very popular publishing. So there's that. There is Go concurrency in actions. I can't remember the name of the author. But aside that, I also listen to like a lot of conference talks about Golang. So I listened to a lot of Rob Pike's talks and just what some other engineers do. So yeah, yeah. So yeah, Go by Packets and Mastering Go. I can't remember the author again. Those books. But I could provide like the links after, like during the networking session. They're not in my head right now. I'm sorry.
Oh, okay, that's fine. Well, we have 3 more questions, but just
Yeah,
one more
I'll
minute.
try as fast as possible.
Yeah, so we have one that says, what you are talking about is really crazy stuff. Can one get to this level of knowledge without engineering work experience? Like actually working in a company? Can I self-learn this without any experience?
Yeah, you can. Like a lot of my Go projects have been like hobby projects. This is a hobby project. No one is paying me to do this. This isn't from work. So yeah, you can learn it if you want to. Yeah.
Okay. So we have another question from Anonymous. Says you use the almanac to get the plant and zombie characteristics. They're mathematically solved with simulations, right?
Well, yes, but not just that. So I used the almanac. I recorded like screen recordings so I could get like more accurate, calculations of what the time representations would look like. And I also there's like if you go to Reddit, there are a lot of Reddit blogs that give like more details on like the speed, the height, the power, the health of all the zombies. So yeah, I did that too. So I went to like so many different sources to gather information.
Oh, okay, okay. So the last question that we have here it says, were you concerned about the number of locks in your solution since it can affect the sims? Okay, it says, were you concerned about the number of person dropped? Okay, it says, were you concerned about the number of locks in your solution since it can affect the system's overall parallelism?
Great. So, in one point, and this, you had like two questions combined into one. So, yes, obviously, I was, but then you need to know when the locks, become a bottleneck for you. So, for me, when the locks were a bottleneck was when counting the frames, because that's like the highest frequency action that's happening in the pipeline. And so for that, I did explore a lockless solution, which was the atomic counters, which are lockless solutions. Outside of that, generally, we when designing concurrent systems, best advice that Rob Pike gives, for instance, is you should try to avoid locks as much as possible, and instead try to structure your systems in such a way that what is happening is simply communication, which is why I made use of channels more. And then at some point, I still had to use the read write mutex because sometimes you just can't, escape that. And so I chose to use the read write mutex because that allowed me to have concurrent reads, which is something that was happening most of the time, and only one write. So yeah, of course I was, but it's about when you get to the bottleneck, then you try to solve it. Yeah.
Okay, I think that's all. The final question says, adding to the previous question, did you explore any lockless solutions to your problem? I think you've answered this
Yeah, I
already.
did. I did. I used the atomic counters. Yeah.
Okay, okay, awesome. So I think that will be all. Thank you very much for your time.
All right.
Really appreciate it.
Yeah,
Yeah,
thank
and also for the attendees, please fill the session feedback form that will be sent to the chat. So, Fanan, thank you very much. Really appreciate your time.
you. All right. You're welcome. Thank you, guys.
Yeah.
Bye.